All right. Good afternoon, everyone. Thank you for coming to this talk. You'll hear about ART, the Android runtime, and all about the new exciting features we've worked on for Android N. I'm Nicolas Joffre, a software engineer in the ART team, and I'll be presenting along my colleagues, Mathieu Chartier and Karine Juravra. So, ART is the software layer between the operating system and the applications. It provides an execution environment to run Android applications. That environment essentially consists of two things. It executes text bytecode, that's the internal Android format of Android applications, through a mix of interpretation and compilation. It also manages memory of those applications, allocating it, and reclaiming it when it's no longer used. Why should you guys care about ART? Well, it turns out ART is at the forefront of the user experience. ART needs to be fast, so that applications can run smoothly. It needs to start applications really quickly to give a snappy experience to the user. It needs to ensure the UI can render at least 60 frames per second to make the user experience jank-free. It needs to be power efficient and not do too much extra work besides executing the application. And it needs to be savvy in terms of memory use. The less memory being used by the runtime, the more applications you can actually run. So if you remember Dalvik, which was the first Android runtime released in Android phones, it was sort of efficient on some of these metrics and sort of OK on a few. At the time, memory footprint was paramount. So we constrained the compiler to not use much memory, and that explains not so great performance. Dalvik also had a relatively unsophisticated garbage collector, and that could lead to long application pauses, leading to a janky experience. So in 2014, we introduced ART. ART shifted the paradigm of doing interpretation and just-in-time compilation at runtime to ahead-of-time compilation when the application is being installed. So when the application is being installed, ART will compile it directly to optimized code. That gave us a great boost on performance in application startup. ART did not need a just-in-time compiler to be warmed up before it could execute. Applications were running out of optimized code directly. And because this code is directly loaded from disk, you don't need to pay the cost of a JIT compilation code cache. The garbage collector has also been completely revamped, where we implemented state-of-the-art concurrent garbage collector algorithms, and we made sure that GC pauses were to a minimal so that the experience was jank-free. Since Lollipop, we've mostly improved on performance. So we have heavily iterated on the compiler. Lollipop, when we shipped Lollipop, it had a quick compiler. That was a fast DEX to machine code compiler. It was ported from the Dalvik JIT at the time. At the time, we were really eager to ship ART, given all the benefits, and we mostly focused on shipping a well-tested and robust compiler. However, Quick was not structurally meant for more sophisticated optimizations, such as inlining and register allocation. So in Marshmallow, we introduced the optimizing compiler. That's a state-of-the-art SSA form-based compiler infrastructure. SSA, in compiler jargon, stands for static signal assignment, and that's a well-known format for doing optimizations in a compiler. We implement all sorts of optimizations, such as inlining, bound check elimination, common sub-expression elimination, and so on. We also implemented a linear scan register allocator, a state-of-the-art register allocation technique for compilers. And in N, we iterated on that compiler and made more aggressive optimizations, like more inlining and lots more optimization. This graph shows the performance of Marshmallow and NPreview normalized to performance in Lollipop. Its benchmarks run on Nexus 9, a tablet where we ship Lollipop, and the first release of Art. And you can see we've constantly improved performance over time. We measured on 3 different kinds of benchmarks. Delta Blue and Richards are a well-known object-oriented benchmark in the object-oriented community that stresses how the runtime implements calls. Drystone is about how the runtime and the compiler generates integer computations. Reversi Bench, Chess Bench, and Ritz are actually adaptations of Android applications. Reversi and Chess emulate the AI of an actual game that you can get downloaded from the Play Store. And Ritz emulates spreadsheet emulation. So we've been very pleased with the improvements we made here, ranging from 1.2x to 5x speedups. And the performance boost isn't specific to one architecture. Because most of our optimizations are CPU independent, all platforms benefit from them. So running the same benchmarks on ARM32 will lead to the same improvement trend across the board. So that's great. Improving the code generated by the compiler is a great win for performance, faster frame rendering, and faster startup. Great. But it looks like you guys run into this. So you're probably familiar with that dialog now. It's pretty lucky, right? Only 21 to go. So that dialog is what is shown when you take a system update. And what happens there, in case you don't know, is that we're redoing all the optimizations we've done at install time of an application. Why? Because when you install an application, Art will optimize it heavily against your platform. And it will put hard-coded dependencies in the compiled code that will make your applications run much faster. But when you get a system update, all those hard-coded dependencies become invalid because you get a new system. So we need to redo all the work. When we shipped Art, that was actually a trade-off we've made because OTAs, or system updates, were usually once a year. So for a once-a-year update, you get yearly better Android experience. But Android ecosystem has evolved. And security being at the heart of Android, our security team worked hard on making sure security fixes could be sent to Android phones as soon as possible. So when our lead security engineer and director of Nexus products announced we are now moving to monthly updates, it was sort of clear that this initial trade-off we've made would not work, and Art needed to adapt. So we brought back a just-in-time compiler in Art. So no more optimizing app dialog. Woohoo! Thank you. It turns out removing that dialog is not the only benefit of having a JIT. We now get much faster installs, around 75% faster. And because AOT could not know when it was compiling which parts of the app is being executed, it turns out that we were compiling all the code of your APK. And that is sort of a waste of your storage if you're going to use just 5 or 10% of the code. But adding a JIT has some unknown. Like clearly, keeping on compiling all the time, like you start the app, you JIT, you kill the app, you start the app again, you JIT. That has some implications on your battery that AOT compile code didn't have. And having a compilation code cache could be wasteful if not managed properly. So what we did in N is introduce a hybrid just-in-time, ahead-of-time compilation system that combines the benefits of both worlds. The idea is that applications start running with a JIT, and when the phone is idle and charging, R will do profile-guided optimizations, and ahead of time heavily optimize the parts of the application the JIT has executed already. So later in this talk, my colleague Colleen will go into more detail about how this hybrid AOT JIT profile-guided compilation works. What I want to focus now is how is the unknown with the JIT. So let's go back to the 5 metrics I mentioned earlier in the talk. For runtime performance, the JIT is based on the same AOT compiler that brings the same high performance. So we're covered. But the other metrics are actually down to how we tune the JIT. A couple of things we made when starting this project, a couple of design decisions we made, were based on those metrics. Like, we implemented a much faster interpreter in N compared to the one in Marshmallow. It runs like up to 3x faster than the interpreter in Marshmallow. It's very important to have a fast interpreter because when you start your app, you don't have any ahead-of-time compile code. It's the interpreter that's going to run, and later on the JIT. Second, we do a JIT compilation on a separate thread and not on the application threads. Some compilation can take very long, and you don't want to block the UI thread just for doing compilation. For saving power, what we do is mostly focusing on the hottest methods of an application. And finally, for memory footprint, we implemented a garbage collection technique that ensures that only the methods that in the end matter over time are kept. So if a method is being compiled and then not being used anymore, we'll remove it from memory. All right. So let's focus on application startup. Now, I'm going to walk you through some systrace that will explain some of the implementation decisions we've made. If you don't know what systrace is, it's a great tool for both app developers and platform developers to analyze what is happening on an Android system. So bear with me. There's a lot of information on that slide, but we'll focus on the things that matter for us. So here's how a systrace looks after launching Gmail on a device that had Gmail ahead of time compiled. So application startup for a user is actually when the first frame is being rendered. And this trace here resembles more or less what you would get on Marshmallow and Lollipop, is that for starting Gmail, it would take half a second for the first frame to be drawn. So our first implementation, our alpha implementation of the JIT, we did the same measurements. And results were not great. You can see now the startup is around 1 second, so we increase the startup around 2x. And you can see that the JIT thread here executing is initially idle, and then becomes very busy. So what's happening? If you take a closer look at what the application is doing, there's around 200 milliseconds for doing just the APK extraction. And doing APK extraction is a blocking operation, so you need to do it before executing any code. Similarly, there's lots of things happening after the APK extraction that don't have to do with executing the application, and that's verification. Art needs to verify the DEX code in order to run it and optimize it. So to fix this problem, we decided to move extraction and verification out of every application startup and move it back to when the application is actually being installed. So this made the application startup 2 times faster than our initial JIT implementation and quite on par with compiled code. So I've just talked about application startup. How about Jank? For Jank, we looked at the frame rate of scrolling within the Google Photos application. And systrace gives you this nice list of frames that are being drawn. A green frame is when the UI managed to render it in time. Orange and red is where you're dropping the frame, and it hasn't been rendered. Now, Jank can be attributed to many factors. And Art does its best at executing the code of the application. But if the application does too much on the thread, obviously we're going to miss a frame. So we have, for that specific experiment, we have around 4% of frames that are being dropped. During our first JIT bring-up, we made the same experiment. So the application wasn't compiled, and we just run it with a JIT. And the results weren't great. We were dropping around 20% of frames. If you take a closer look at what the JIT is actually doing here, you can see those long compilation activities where the compiler is actually waiting for methods or for requests to compile methods. Those methods haven't reached the hotness threshold that we've set. And the hotness threshold is high because we want to save on battery, but that doesn't save on saving Jank. The UI thread, you want the code that thread is executing to be hot as soon as possible. So the solution was to increase the weight of UI thread requests for compilation. So the methods it runs would be compiled almost instantly. So if you see in the issue trace, there's no more long pauses of compilations, and we only dropped around 4% of frames, which was the AOT level we had initially. All right, battery usage. We've measured the power usage of starting Gmail, pausing for 30 seconds, and then scroll around the emails. And we can see here that the JIT is paying a high cost at application startup compared to ahead-of-time compilation. But once startup is done, the scrolling actually has no difference between AOT and JIT. The reason for this difference is that at the startup, the JIT is very busy compiling a lot of methods. And Gmail seems to be very aggressive in executing code at startup, which is not necessarily the behavior of all apps. So we've done the same experiment with the other apps. We've looked at Chrome, Camera, and Photos. Chrome and Camera are mostly based on native code. So here the JIT is not really useful for all the things we mentioned. And the power usage is very similar whether you're in an AOT setup or a JIT setup. Photos, on the other hand, does have Java code, but doesn't have the behavior that Gmail had. And you can see that the difference is, again, very little. That was battery. Let's discuss about the final metric, memory footprint. So we looked at the overall usage of our beta testers within Google. And we're quite happy to find that the memory use of the JIT is fairly reasonable. The maximum we've seen on a heavily loaded system that had lots of applications being executed was around 30 megabytes, system-wide. But in average, what we've seen is that it's in general 10 megabytes. For individual applications, big Java applications will take some memory, like 4 megabytes. But in average, most applications have a reasonable Java code size and the code cache is fairly small, around 300 kilobytes. So to wrap up on how JIT affects these metrics when it's being executed, we've seen that performance and jank are on par with the quality level we had with ART ahead-of-time compilation. And I've shown you that it does have a relative impact on application startup, battery, and memory footprint. So now, I'll be handing it over to my colleague, Colleen, and he's going to explain to you how we're recovering from those small regressions compared to AOT by doing idle-time profile-guided compilation.
Thank you, Nicola. Hello, everyone. I'm Colleen, and I'm here today to give you more details on profile-guided compilation. And this is a new compilation strategy that we introduced in N, and as my colleague Nicola mentioned, is a combination between JIT and ahead-of-time compilation. And it's mainly based on the observation that the percentage of the application's code, which is actually worth optimizing, is very small in practice. And focusing on the most important part of the application drives a lot of benefits for the overall system performance, and not only limited to recovering the slight regression that we have to an AOT system. So the goal here was to have a full 5-star system, and this is what profile-guided compilations help us achieve. So let's take a look a bit on the idea. In a nutshell, we want to combine execution profiles with ahead-of-time compilation, and that will lead to a profile-guided compilation. What that means is that during application execution, we will record profile information about how the app is executed, and we will use that information to drive offline optimizations at a time when the device is charging and idling, so that we don't take resources out of our users. So let's take a look into more details how this works, how it affects the lifecycle of the application, and how it fits together in the JIT system that my colleague talked about. The first time the application is executed, the runtime will interpret it. The JIT system will kick in and optimize the hot methods, and eventually this cycle will repeat. In parallel with the interpretation and with the JIT compilation, we record the profile information. And this profile information gets dumped to disk at regular interval of times. The next time that you execute the app, the same process starts again. And the profile files will eventually be expanded with new use cases based on how the user used the app. At a later point, when the device is not in use anymore, it's idling and charging, and it's a state that we call maintenance mode, we kick in a service. And what this service does, it takes a look at the application, it looks at the profiles, and it tries to optimize the application based on its use. The output of the service is actually a compiled binary. And this compiled binary will replace the initial application in the system. So now, the next time the application is launched after this service will executed, the application will contain different codes, different states of the same code. So you may have code which is interpreted and eventually be JITted, and you also have code which is ahead of time compiled. If the user, for example, uses a new part of the application that haven't been explored before, that part will be interpreted and JITted and will generate a new profile information. And so the cycle begins again. So what's important here is we'll improve the application performance as the user executes it with new use cases. And we'll keep recompile it until we discover all possible cases. So let's focus a bit on the profile collection and how that impacts the application performance and other factors. As I mentioned, we do collect them in parallel with the application execution. And what we focused on to make sure that it has a minimal impact on the performance. And one factor that we put a lot of attention into is to have an efficient caching and I/O throttling so that we minimize the write operation to disk. We also have a very small file footprint, and the amount of data that we write to disk is actually very, very small. Another point, which I mentioned before, is that we keep expanding these profiles as the app executes. And obviously, it depends on the application. It depends on the use case. Our test shows that the largest part of the data is actually captured during the first run. Subsequent runs add to the profile information. It obviously depends how the user used the app. But the largest chunk of the information is actually captured during the first execution. And that gives us important data to work on. A final point which is worth mentioning here is that all the application, all the users get their own profiles. And with that in mind, let's take a look on what exactly we record in this profile information. The first thing are the hot methods. And what constitutes a hot method? It's a metric which you have internal to the runtime. And factors that contribute to it are, for example, number of invocations, or whether or not that method is executed on the UI thread, so that you can speed up requests that will impact the users directly. We use this information to drive offline optimizations and to dedicate more time to optimize those methods. The second data that we record are the classes which impact the startup times. How do we know they do so? It means that they are loaded in the first few seconds after the user launched that app. And my colleague Matthew will go into more details on how we use that to improve startup times even more. A final piece of information that we record is whether or not the application code is loaded in some other apps. And that's very important to know because it means that the application behaves more like a shared library. And when it does so, we'll use a different compilation strategy to optimize it. So let's focus now on the compilation daemon, on the service that actually does the compilation. And let's take a look on what decision it makes. This is a service which is started at boot time by the system, and it's scheduled for daily run. Its main job is to iterate through all the APKs installed in the system and figure out whether or not we need to compile them, and if we do need to compile them, what sort of strategy we should use. The service wakes up when the device becomes idle in charging, and the main reason for that is that we don't want to use user time when the device is active, and we don't want to waste battery time. So we delay this until the device is not in use anymore. When the daemon wakes up, what it does, it iterates with the applications, and the first question it asks is whether or not the application code has been used by some other apps, that data that I was telling you that we record in the profile. If that's the case, then we perform a full compilation to make sure that all the users benefit of the optimized code. If it's not, and this is the case probably for the largest percentage of the apps, it's a regular app, you don't get used by some other apps, we go into and perform a much deeper analysis on the profile information. If we have enough new data, if we collected enough information about the application, then we will profile guide compile that application. We'll take a look at the profiles, and we optimize only the methods that were executed so that we focus on what actually the user used from that application. If by any chance we don't have enough information, let's say we only have data about one single method from that app, then we'll just skip it because probably it's not worth optimizing. And an important thing here is that we do perform the profile analysis every time that we run the daemon. And what that means is that we might end up recompile the app again and again until we no longer have any new information about it. And here you can see that actually I was talking about different use cases and how we apply different compilation strategies. Shared libraries get a full compilation, whereas the regular apps prefer a profile-guided compilation. In N, we generalized on that. And different use cases from the lifecycle of the application have different compilation strategies. For example, at install time, we don't have profile information, yet we still want the application to start as fast as possible. And as my colleague Nicola mentioned, we have a strategy where we extract and verify that app with minimal running time, and which will ensure that the application starts fast. When you update the app, we have the same story. We no longer have a profile because what we recorded before was invalid. So we repeat this verification procedure. When the compilation daemon kicks in, we'll do a profile-guided compilation where possible. And for system and shared libraries, we're going to do a full compilation so that we make sure that all their users are properly optimized. With that in mind, let's take a more closer look on what benefits are when we do profile-guided compilation. And all the benefits share the same root cause. We only optimize what is being used. And what that means, when you first start the app after the compilation happened, previous hard code is already optimized. We no longer have to wait for the JIT, for the methods to become hot so that the JIT can compile them. So the applications will start faster. We have also less work for the JIT, and that means we use less CPU, and we increase the battery life overall. And because we are much more selective with what we optimize, we can dedicate and spend more time there and apply more optimizations. Besides that, we get a smaller size for the compiled binary. And that's a very important thing, because what we do with this binary, we map it into memory. Smaller size translates to reduced memory footprint. And the important difference here is that, for example, this memory that we map into, this binary that we map into memory will be a clean memory compared to dirty memory that the JIT will generate. We also use far less disk space because the binaries are much smaller now, and we free a lot of space for our users. How much space? Let's take a look at the numbers. In this chart, we compare different applications, which is Google+, Play Music, and Hangouts. And we tracked how the generated binary for the compiled code performs across Marshmallow, which is the blue line, and Preview during the first boot, which is equivalent to a fresh install of the application, which is the orange line. And the green line is how much it takes for the profile-guided compilation. As you can see, the reduction is more than 50%. And obviously, the green line will go up over time. And our test shows that actually it stays around 50% most of the times. And you may wonder how come we get so great reduction in terms of size. Well, when we analyze the profiles, we've realized that only 4 to 5% of the methods actually get compiled. And as you use the app more, obviously this percentage will go up, will generate more code. But as I said, in general, we'll stay below 50% or around that area. Now, a natural question here is, if I'm only compiling 5% of the app, how come I reduce the space only by 50%? Why not 95%? Well, those lines contains also the application raw code, the DEX code. And that's a line below which we cannot go, because we need to run something. And here is how we compare to the application size. You can see that in Marshmallow, we generated more than 3x in terms of code size, whereas in M, we stay below 1.5x. And these are all cool benefits, but it's not the only thing actually that we use profiles for. We also use them to further speed up system updates. As my colleague Nicola mentioned, because of JIT, we don't need to recompile the app again. And that basically gets rid of the long waiting time for the optimizing app. We still want to do some processing of the app, in particular extraction and verification, to ensure that those apps get executed as fast as possible when they are first launched. And in M, we actually know how those apps were executed before. So we can use profile when we guide to guide the verification. And that saves around 30% of the time extra. We also added new improved usage stats. And compared to M, we can now track precisely how the application was used and how it was executed. And we only analyze what actually matters for the users. What is that? Application which has a user interface, and the users can interact with them. Those are the most valuable for our users, and we focus on them during system updates. However, when you take the first update to M, we don't have access to all the goodies. We don't have profiles, and we don't have enough accurate user stats to realize how the app was used. And what we do a full verification of most of the apps. This is still much, much faster than we used to do in M. And how much faster? Let's take a look at the numbers. You can see here 3 different lines, and these numbers are obtained on the same device, which have roughly 100 applications installed. And the first line, which represents an OTA, a system update from M to M prime, where we took a security update, we took around 14 minutes to process all the applications, and that's the time that the runtime spends processing them. When we take the OTA to N, we reduce the time to about 3 minutes, which is around up to 5x reduction. And there we verify most of the applications. Now the next step, a security update will kick in for N. And what we do, we already have profile information, we already have improved usage stats. And we can use that to drive that time even lower. And when you take a security update on this device, we take less than a minute. And compared to M, that's more than 12x improvement in terms of speed up. With that, I'd like it to pass it to Matthew, and he will explain how we use profiles to further to speed up application even more.
Thank you, Colleen. One new feature in N that reduces application launch time is application images. An application image is a serialized heap consisting of pre-initialized classes. This image is loaded by the application during launch. During launch, most applications end up loading many classes for initialization work, such as creating views or inflating layouts. Unfortunately, loading classes is not free and can consist of a large portion of the application launch time. The way that application images reduces this cost is by effectively shifting work from application launch time to compile time. Since the classes inside of the application image are pre-initialized, this means they're able to be accessed right off the bat by the application. Application images are generated during the background compilation phase, I think what Colleen referred to as a maintenance phase, by the AOT compiler. Leveraging the JIT profiles, the application images include and serialize only the set of classes that were used during prior launches of the application. Using the profile is also key to having a small application image, since it only includes a small fraction of the classes inside of the actual application. Having a small application image is important because the application image is resident in RAM for the entire lifetime of the application, as well as larger images take longer to load. As you can see here, application images have a very low storage requirement. This is mostly due to the profile. For the 4 apps here, the storage requirements were less than 2 megabytes per app. As a comparison, I put the application, compiled the application code with the profile, so this is already reduced compared to what application code sizes would have been on M. The loading process of application images begins with the application class loader creation. When the application class loader is created, we load the application image from storage and decompress it into RAM. For dynamically loaded DEX files, we also verify that the class loader is a supported type. Since there is no dependency from the application compiled code to the image, it means that we can reject the image. So if the class loader is not supported, we simply reject the image and resume execution. Here are some results for application image launch time improvements for the 4 apps that I had just displayed. As you can see here, there's around a 5 to 20% improvement compared to profile-guided compilation only. And now to the garbage collector. The garbage collector has not changed too much since our last I/O presentation. As you can see here, we were already in pretty good shape back then. There is still only one short GC pause, and the garbage collector has high throughput since it is generational. There have been a few GC changes, mostly related to application images and class unloading. However, these GC changes do not have substantial performance impact. One thing that has improved each release is allocation time. With L, we introduced a new custom thread local allocator that reduced allocation time substantially by avoiding synchronization costs. In M, we removed all the compare and swap operations in the allocation comment case. Finally, in N, the allocation comment case has been written in hand-optimized assembly code. This is the largest speed up yet at over 200% compared to M. Combined, all these improvements mean that allocations are now around 10x faster than KitKat, which was Dalvik. Class unloading, also introduced in N, is a way to reduce RAM for modular applications. Basically, what this means is that classes and class loaders can be freed by the GC when they're no longer used. In previous Android versions, these were held live for the entire lifetime of the application. For class loading to occur, all the classes in the class loader must no longer be reachable, as well as the class loader itself. When the GC notices this, it frees them, as well as the associated metadata. This chart demonstrates just a bit of how the class loader interacts with other components and retains them. With that, off to Nicholas for the wrap-up.
Thank you, Matthew. All right, so to wrap up, we've shown you all the features we worked on for N, mainly a faster compiler, up to 5x compared to previous releases, a faster interpreter, up to 3x compared to Marshmallow, a new JIT compiler, and profile-guided compilation that just removes that optimizing apps dialog and provides faster installs. Applications image for faster startup, and faster allocations. You can actually, if you're interested in all that sort of low-level stuff, follow it on the AOSP website, where we actually do all the development. With that, we'll take your questions. Thank you.